So I have to first acknowledge the help of everybody who have been helping us with the data that I'm going to show. So it has been, I'm going to show a wide range of data. So it has been a collaboration between different national labs and different institutions. And of course, I have to thank my team as well at Duke, who have been working hard on this. And Jin Zhongxi, he has been actually leading the data that I'm going to show you. Okay, so a very brief introduction onto Shastri-Sutherland model. So if you want to go very simple, Hamiltonian, J and J prime are both going to be antiferromagnetic, so Heisenberg interaction, nearest neighbors, next nearest neighbors. Now, what is neat about this is that there can be two different cases, two extreme cases, depending on the ratio between J and J prime. So it's a frustrated magnet by the sense of when you have a competition between the nearest neighbors and next nearest neighbors. So the good thing is that the ground state is exactly solved. So that's, as an experimentalist for me and for the theorists, it's very helpful so that if we can find a real world realization of the system, at least we know more or less what's going to happen with the Hamiltonian. So here's the J prime over J. If it's much less than 0.69, so this came from Shastri-Sutherland model, then what they're predicting is that the ground state is an isolated singlet, okay? Then in the other extreme case, if J prime is much stronger than J, it's more than 0.85, then the ground state is an ordered Néel antiferromagnet. Now, initially it was thought that this transition is happening directly, but then it was not long-lived because our good theorist collaborators and everybody who has been working on this, they figured out that this is not so much of a direct transition, and there's this very interesting plaquette state or an intermediate state which is connecting these two. So up to this day, this is more or less still a question mark, but we have been able to actually accomplish some good progress with regard to understanding what is the state of this plaquette state. Now, as an experimentalist, for me, it's important to be able to have a sample in my hand and be able to do an experiment on it. So the system I'm going to talk about is strontium copper borate. So copper 2+ carrying spin 1/2 is responsible for magnetization in this compound. So what you are seeing here is coppers in red, and they are forming these orthogonal dimers. J is the nearest neighbor interaction, J prime next nearest neighbor interaction. So you can see these orthogonal dimers. Topologically, we can map this into a Shastri-Sutherland system, because if you just look at the Shastri-Sutherland model and you rotate it, you can now start to see these, orthogonal dimers. What is quite interesting about this particular compound is that its J prime over J is 0.63. So when you just look at it and without manipulating anything, it's going to be in this singlet state, according to Shastri-Sutherland, because less than 0.69. But look at this, it's pretty close to that transition. So it can be a candidate for us to be able to manipulate this J prime over J, either by application of pressure, chemical doping, or even magnetic field, to be able to map the phase diagram and have a better understanding of what is happening, okay? Now, the first step is to figure out, is this really a singlet ground state? And the way that you can do that is very quickly. You can look at it with inelastic neutrons. So this is what I'm showing here. This is energy as a function of Q. And at 3 MeV, there is this excitation happening, which is a singlet triplet excitation. So it's a singlet ground state. And this is a multi-bound excitations of multi-triplets. Now, if you make a cut, for example, here at a particular Q at low temperatures, you can see that 3 MeV singlet triplet excitations, the multi-triplet excitations, when we start to warming up, you're populating all the singlets into triplet, so there's nothing to be captured here. What was also interesting is that if you now, this is no application of magnetic field even. So if you start to look at this with very high resolution neutron scattering, even in the absence of magnetic field, you can see that the triplet state is, the degeneracy of it is lifted. So you would expect that, okay, so your S equals to 0, plus and minus 1, they should be degenerate when you have no magnetic field. However, this listing of the degeneracy was then later on proposed as the existence of the DM interactions. So this system has DM interactions, and the DM interactions are actually quite important. So before I go into extreme magnetic fields, I'm just going to introduce these two papers, which you may be interested. So they're talking about the fact of that then now the triplets, they have the DM interactions into them. And in the low magnetic field region, there can be a critical field that can start to show these triplons in these dimerized quantum magnet that are forming sort of like a Hall effect. So this is something that we are starting to look into that. So this is a theory paper. So we are starting to look into see if we can actually capture this with thermal Hall measurements. But this is a combination of a theory and experimental paper with inelastic neutron and even at higher resolution, and they start to apply magnetic fields, not very high, up to 2.8. And they also are saying that there are some topological triplon modes in the bound state of the triplets, just for you in case you're interested in having a look into the topological features of this compound. Now, going back, so people have been quite interested in this compound, not only because it has this close relationship with the tuning of the magnetic field or pressure to be able to map the phase diagram, study quantum phase transitions, but also this nature of the plaquette singlet state. So so this is mainly being driven by the theorists who have been very interested in that. So there have been papers out there, actually quite even recently, because of the advances in the experimental part, that they talk about various types of natures. So for example, is it an empty plaquette, or is it a Haldane plaquette, which I will explain a little bit later. So this is a recent paper by Frederick, who have been explaining various types of scenarios. Now, as an experimentalist, another way to look at this is application of pressure, right? So by application of pressure, these are the very first data that came out from Japan. And what they have been able to do is look at the susceptibility as a function of temperature. So if you're dealing with a singlet ground state at the absence of any pressure, you're getting into a singlet state, which is a non-magnetic, so it's going to be 0. And as you start to warm it up, then you're getting it into this populated triplet paramagnet phase. But if you start to apply pressure, what is happening is that even at very low temperatures, no longer you have a zero susceptibility. However, you start to see that there's some infinite number here at 0.9 GPa. If you even go higher, you can see that the gap starts to close down. So at that time, actually, most of the pressure cells, they could only get to 1.4 GPa. So this by itself was just a phenomenon, and it was very intriguing to other experimentalists to be able to push this even further. So at the time, actually, I was at Argonne National Lab and University of Chicago, and we had access to these diamond anvil cells and the synchrotron X-rays, which means that you can use the diamond anvil cells to get even above these 1.9 or 2 GPa to be able to look at what the lattice is doing. From the data that I'm not showing here, we also knew that there's a very strong spin-phonon coupling in this compound. So what we decided to do was, okay, so let's look to see what the lattice is doing if we start to go really high in pressure. So here you're looking at the diamond anvil cell. This is the sample chamber. So it's practically, these are the two dimers. This is what I'm showing in here. This is the sample, silver for low temperature calibrations and ruby for high temperature calibrations of pressure. So what we noticed was actually quite interesting. What we noticed is that if you just look at the susceptibility data and we plot 1 over A, so A and B and C are the lattice parameters. So A and B is the plane where you have your dimers in them, and it is tetragonal, so they're equal, at least at 0 pressure. We saw that they trace pretty well with the susceptibility data. However, what is quite interesting again is that when we start to cool it down, you would expect that because the sample is shrinking, so the A should start to become smaller. But we saw actually the opposite. We saw that A starts to go up. So the system, as it gets into this singlet ground state and the formation of the dimers, they will extend at least in the A direction. So this showed that there is this very strong spin-phonon coupling, and we were able to reproduce this data indirectly by extracting magnetism off of the lattice. However, the next step is now to even push it even higher in pressure. So at that time at Oak Ridge National Lab, they have a particular beamline dedicated for high pressure experiments. And we were able to actually look at, this was, I believe this was the first single crystal experiment done at SNAP. So what we were able to do is we said, okay, so let's assume that this ordered phase, a nail ordered phase is going to happen if we start to push it even higher in pressure. So what we would expect is to see these Bragg peaks, magnetic Bragg peaks popping up that would correspond to this nail antiferromagnetic state. So we started to look at the forbidden peaks, which were nuclearly forbidden, and we started to cool down the sample. And what we noticed is that, yes, when we are at 5.5 GPa, or I would say at above 4.5 GPa, you start to see these peaks popping up, which they correspond to the same structure that was previously proposed by Shasta and Sutherland. While if you sit at, for example, and a load Bragg peak, there's not so much of a transition as a function of temperature, okay? So this was later on actually, and this is just the data that I just showed you. We were able to practically map it as a function of gap by fitting our data to a power law. And we're just showing that at around 2 GPa, it looks like there is going to be some sort of a transition from a singlet to this intermediate phase. So later on, this data was published, which again agrees with what we saw. So this, however, has a bit of piece of information, which is also very important. So what they notice is that this is with neutron data. So there is this 2 GPa, the transition from a singlet to a plaquette state. However, in a plaquette state, you can see that they saw two modes. One, which they called it still the gap, so the gap doesn't close completely, but also there is this LE or low energy mode that they also noticed. And as they go above the 4.5 or 4 GPa, they also saw that there's this transition to this ordered phase. Okay. Now, okay, so this is just the pressure. So what's going to happen if you start to apply magnetic field as well? So if you have a singlet triplet state, so what will happen is that you, from the Zeeman effect, the triplets start to actually branch off, and then there would be some sort of a critical field that you will have your triplet crossing the singlet state. So in this scenario, your singlets are going to be basically like vacuum. Triplets are bosons with this hardcore repulsion, and magnetic field is practically the chemical potential. So we can start to study these and adding this Zeeman effect into the Hamiltonian to figure out what's going to happen. Okay? Which practically is what we did here. So here you're looking at the data, inelastic neutron scattering data, energy as a function of Q, zero field, this is the 3 MeV single triplet excitations. At 3.5, you can see the separation. At 7 Tesla, even further. So what it's showing is that, okay, the really high magnetic fields are needed to be able to get to this, or even start to see what's going to happen when you start to cross these singlet states. And this is what happened. So there are actually a lot of data for decades that have been published, both experimentally and from the theory point of view, because it's so rich. So you can see that folks have been able to go, these days actually even 100 Tesla in Japan, to look to see what's going to happen. So here's the HC1, but it is actually, for this compound, is rather higher than what you would expect from theoretical. If you just put gap equal to G mu BH, so it's a little bit higher, but there are these plateaus that are popping up that are quite interesting. So initially what was taught is that these plateaus correspond to this formation or crystallization of S equal 1. For example, when you have the 1/8, then you would have 1 out of the 8 nets that are going to be these triplets. But later on, Frederick Miller and actually Philippe Cobos, what they discovered was that it's not so much an S equal to 1 that are forming these crystallizations at 1/8, 1/3, and 1/4 of the magnetization, but there are these bound state of these triplets that are forming these. Okay? Now, from our point of view, so it was okay, So it looks like that at least what we know what's happening as a function of magnetic field, but also we have pressure. So let's see what will happen if we start to squeeze the sample in high magnetic fields or getting into this plaquette state and see what's going to happen there. So this is our pressure cell, and this is the sample. So the technique we had to use is called the tunnel diode oscillator technique. And the reason that we use it is because it's so high resolution. Typically it's used for looking at quantum oscillations, not so much magnetism. But in our case, we decided to look at that. So your sample is going to be in a coil, and we look at the resonance frequency of this coil. So it's an LC circuit, and practically when the magnetization of the sample changes, then what is changing is the inductor of the LC circuit. So if you look at the resonance frequency, you would be able to see how it's changing. So delta F over F is practically going to be related to dm over dh, or susceptibility. It's so high resolution, and it's important because the pressure cell and the sample are going to be very small. So it's a spin-a-half compound. For us to be able to have some good signal to noise ratio, we needed to find a good technique for it. So here's the data that you can see. So first of all, we have to have some sort of like a relationship between this TDO and just conventional magnetization measurements. And this is just a conventional magnetization measurement at zero pressure. And this is the TDO, the derivative of TDO. So it's a second derivative of magnetization. And both of them are showing that at around 27 Tesla, there's a 1.8 plateau. So it looks like, okay, so we can use this technique to be able to map what the 1.8, for example, is doing. So if you look at zero, this is the 1.8 plateau, which is the first major plateau in this compound at around 27 Tesla. But when we start to go up in pressure, it starts to move down in magnetic field. The moment we pass the 2 GPa critical point, we start to see a new set of plateaus that are popping out. So this was actually quite interesting because it's a signature of the plaquette state. So at that time, we were actually collaborating with Christian Battista, and what they were discovered was that if they do a DMRG calculations, then what they can say, okay, in the case of the 1.8 plateau, this prediction by Frederick Miller and Philip Cobos is actually standing in this particular case as well, even though that was with IPEPs, and this is GMRG. So there's these bound states of triplets that are forming this sort of a crystallization. However, when you look at this particular plateau, what we do, or I should call it anomaly, because not so much of a plateau, this anomaly, actually, they started to say, okay, there's some sort of a stripe ordering happening in here. But this is, we were not able to actually directly figure out what is going on in here. So this is just a simulation from theory point of view. How much more time do I have? Okay, so because I only have 5 minutes, I'm gonna rush through 10 minutes. Oh, thank God. Okay, so because, well, I have the guy who did the calculation sitting here. So, okay, so right. So what we discovered, what we thought that would be interesting to do was to start to look at these particular phase that is happening at, so these are all for the pure compound, only as a function of pressure. So here you're looking at very low pressure, so, and then we start to go up. So this is the 2 GPa that I showed you, but we started to actually go even higher in pressure, so deeper into the plaquette state. And what we notice is that this 7 or 6 Tesla anomaly actually starts to show this doubling. And this doubling, if we start to look at this as a function of temperature, is actually, I think it's only resists up to 500 millikelvin. I will show you the data. But also what we did, we went to even higher magnetic field. So this goes up to 45 Tesla. And we started to map out, for example, the 1.8 doing and what the 1/4 doing and the 1/3 doing. So what we can say is that while the 1.8 plateau, it starts to actually come down as a function of field and as a function of pressure, and it starts to kind of plateauing. But what we notice is that the 1/4 plateau starts to keep coming down as we go up in pressure, and so it ends up even at lower magnetic fields. So it looks like something is happening here that could be interesting, and we may be able to find some more physics, underlying physics of this compound. this doubling here, when we look at these LE modes and the gap, we thought probably that could be related to this. And then later on, I will show you how we think that it is mapping to exactly this mode. Okay. So here, what you're looking is, I'm showing you, this is the pressure and this is the gap. So we started to convert our field to gap energy. And here you're looking at the, so this is practically, so let's start from here. So this is the magnetic field as a function of pressure. And I'm tracing 1/8, 1/4, 1/3, and also the LE mode, the one that is happening as at a lower magnetic field. So you're seeing that what is happening, so these guys starts to move down. This is plateauing. This is also moving down. The LE mode starts to actually to happen at around 6 or 7 Tesla, but also it starts to double, okay? Then if you now map this into the energy, so everything is now as a function of energy MeV and as a function of pressure. This is the neutron data that I show you, the Nature Physics paper. This is a new heat capacity data that they were able to actually do exactly the same thing. And this is our TDO data. So we can see that everything is mapping out pretty well. So our TDO data also maps with this. However, what we notice is here is that the LE mode, and there's this, this doubling of LE node happening as we go deeper into the plaquette state. So what we think is that because the gap starts to come down, so most likely, so again, this is as an experimental, so most likely just reading the theory papers, it could be indications and a signature of the plaquette state is not an empty plaquette state. So it could be the Haldane state. But so this still needs to be looked into more carefully. Now, so here, this is the data as a function of doping. So look at this. So we have these coppers that are forming these dimers. Now, what will happen if we start to substitute these coppers with something non-magnetic, like magnesium? So it's practically like punching a hole in there and breaking some of these dimers. So what we decided to do was then we start to look to see if you have some free spin sitting there, like an agent, what are they going to do? What's the physics of it? And practically what we notice is that, okay, so the 1/8 is not gonna show much of a difference in here. So this is a magnetization as a function of a field. So here you can see that there's not so much happening in there. However, if we start to look more carefully at lower magnetic fields around here, you can see that at 5%, 3%, and 2%, the higher we go in doping, there are new plateaus, new anomalies that are popping up in here, okay? So this is dm over dh. Now, this is the measurement done with magnetization because it's zero pressure, so we could use a larger sample. But then if we do the TDO as well, so you can see that they map exactly with the same anomalies that we saw before. So if you do magnetostriction measurements, however, we didn't see so much of happening with there as a function of doping. So whatever these guys are, they are not going to be so much coupled into the lattice. That was what we discovered. Okay, so this is where now Frederick and Philip came to our rescue to figure out what's going on here. So what they discovered was that these 3 states, which I believe Philip is going to talk about this in more details, what they discovered is that these 3 new, let's call it in gap or a new plateau lower field anomalies are going to be corresponding to 3 different states. So one of them is going to be the formation of some S equal to 1 triplets. When you have both of the dimers, when you have 2 free spins sitting on 1 dimer, one of them is going to be, again, as what we had before, these bound state of triplets. And one of them is actually going to be a special case when you have these bound impurities or the holes that are forming these bound states. So if we now think about these 3 states and we start to look at them, and so here again, it's just shown in better HC1, HC2, and HC3, and we start to look at them as a function of temperature, you can see that, for example, here, what we have here is a field as this is as a function of pressure. So what we see, for example, here is that these in gap states start to also do more or less the same type of a behavior as we saw for the pure system. Here it looks like there is some sort of a jumping happening, but we are not quite sure. The doubling is softened though. So there are 3 new states that emerge. The dependence to the pressure is more or less the same as what we saw for the 1.8. However, the doubling is not so much in there anymore. Now, this is our data when we started to again plot it as a function of energy for everything that we had, including the dopes compound for the 5%. And you can see that more or less when you're looking at the gap, there are not so much, it's a little bit lower gap when you have it doped. However, in this case, you can see that there is not so much of a splitting happening in there. Now, this is showing the splitting that I just explained to you when we start to look at it as a function of different doping and as at different pressures. So here, for example, you can see even when we were at 5%, because the pressure was a little bit higher, we start to see a shadow of this splitting. So whatever this splitting is, it happens when we are really deep into the plaquette state. And what I should also note is that the LE mode, it disappears at about, it's 800 millikelvin. So when we go to very high temperatures, it's not there. And that actually couldn't be an explanation why it was not seen, for example, in neutron data, or it was not seen before, because you need really low magnetic fields. Now, here I'm showing you the new data that we have from neutron experiments under high pressure, because really in order to figure out what's going on, for us is to be able to look at neutron experiments. So this is a diffraction experiment, it's pretty new. So we use a new type of a pressure cell, which is called the hybrid pressure cell. So this can literally go up to 4 GPa. Well, we reached 4 GPa and it exploded. So below 4 GPa. So that's what I can tell you. And this is the size of the sample. So it's actually quite interesting because the size of the sample can be actually rather large in these compounds. And for neutron experiments, we really need it large. So here we started to look at, again, the Bragg positions that we discovered are going to be interesting if we go for the scenarios that are already out there. So one of the scenarios out there was actually published earlier by Christian Batista's group. And they discovered that, okay, if you start to apply magnetic field and in a plaquette state, there may be this scenario that there's some sort of a stripe ordering that's happening. So this is what we did. We went to these Bragg reflections that are corresponding to this stripe ordering, and we started to look at it as a function of field. And actually what we discovered is quite interesting. When we start to, when we are at no magnetic field, which is in black, there's a Bragg peak there because of the nuclear interactions. But when we start to go up at 7 Tesla, when we have the first anomaly, then we start to see that there's an enhanced Bragg peak in here. So it could be that, yes, there is some sort of a stripe ordering happening that as a function of field, it starts to go up. So this paper just recently came out, and again is suggesting by, in collaboration with Frederick, so they are again producing some sort of a scenario that in the plaquette state, there may be a situation that there is this sort of ordering, that this again agrees with the data that we saw. But we have a follow-up experiment, so we should be able to look at more Bragg peaks to be able to figure out, is this really truly the nature of the plaquette state or not? So here I'm just showing you different Bragg peaks and how they are moving as a function of field. And what is also interesting is that we were able to map the pressure to the J prime over J, because most theories, they go with J prime over J. And it looks like that actually, if we map it to the J prime over J, it agrees with what they are predicting, that just deep into the plaquette state, just shy of 0.7, there is going to be this splitting. So now the question out there is, what is the nature of this splitting? What truly is happening when we are above the 2.0 GPa? Are there any sort of symmetry breaking? Is there any DM interactions that are kicking in? So what is, at the end of the day, what is the nature of the plaquette state? Is it this plaquette 2 triplons, or what's going on? Okay, I just leave you with the conclusions that frustrated magnets are important. We need theories to be able to expand our sample synthesis, sample design, and experimental techniques. From the experimental point of view, sample environment is always important. Thank you.
Thank you very much. Questions?
Yes.
So I'm going to repeat the question. So, what's the Haldane state?
So according to what I understand is this scenario that when you have these, the half of the nearest neighbors have anti-parallel spins and the remaining half have parallel spins. This is the Haldane that they're proposing. But this is a new paper that came out, so it's explained here actually pretty well. So they start by empty state, empty placket, and then there is actually some, because there's this pantograph mode frequencies that they also map into these DFT calculations, and they came, at the end, this is more or less, it looks like that this is the likeliest scenario. If you read this paper. Yes, yes.
So actually, I have one. So what's known, like if you tune pressure and magnetic field, like how much is the system still described by the Sutherland model, or
on the magnetic field? Or
yeah,
pressure?
also on the pressure, yeah.
Up to 2 GPa, it's still Shasta-Sutherland. What do you mean by Shasta-Sutherland?
No, they're just a simple 2D.
Okay, so it's a little bit tricky because when we go to very low temperatures, when it starts to dimerize, then it starts to buckle. So it's not so much like a 2D, it's a quasi 2D. But still, you can put the Shasta-Sutherland plug interactions in there and can explain it pretty well. When we start to get to the 2 GPa, then you get into the plaquette state, which is a question mark and a developing field. But when we get to the very high pressures, then antiferromagnetic state is there, but again, it is buckled. So it's a quasi 3D actually at that point.
Okay, well, yeah, thank you very much.